We'll start in 1 minute. Today we'll start section 4.1, part A, on systems of linear equations. Okay, so this is the simplest form of a system of linear equations. So in particular, we'll be looking at systems of two linear equations in two variables. But just for your information, in general, you could have a system of n linear equations in n variables. So this is as easy as it ever gets. The first sentence, a solution to a system of two linear equations in the variables x and y is an ordered pair, x comma y in parentheses, that satisfies the conditions of both equations. So I'll demonstrate how this works. We can also say a solution to a system of two linear equations is a point on each line. Remember, if you have a linear equation, you can graph it, and the graph is a straight line. So if a system of two linear equations has a solution, that solution corresponds to a point that is on each of the two lines. And what does that mean graphically? Graphically, a solution to a system of two linear equations is a point where the two lines intersect. So these three sentences are all interrelated. A term that you'll need to be familiar with, a consistent system of two linear equations has at least one solution. And an inconsistent system of two linear equations has no solution. So in this space below, I'll illustrate the possibilities for systems of two linear equations that are either consistent or inconsistent. So we'll have three examples. So I'll draw three sets of x and y axes. Okay, first one on the left. If we graph two linear equations that have different slopes, so this is just one way I could draw a line. And suppose there's another line with a different slope, So in this graph, one of the slopes is positive and the other one is negative. But this is just an illustration. It could be the case that both slopes are positive and both are negative. But as long as the slopes are different, if the slopes of two lines are different, they will intersect at exactly one point. So the ordered pair for that point, whatever those numbers happen to be, x comma y in parentheses, this ordered pair is a solution to the system of two linear equations. So the system in this picture has one solution. And so this system is consistent because it has one solution. The definition of consistent is that it has at least one solution. Okay, so that's labeled down here, one solution, consistent. The next one will illustrate infinitely many solutions. So if a system of two linear equations has infinitely many solutions, what do you suppose must be true about the two lines? Parallel lines never intersect.
They're the same line.
The same line, yeah. So if you have one line in the xy plane, and if the other line is exactly the same line, so if they're the same line, you wouldn't be able to tell the difference. But I've tried to show you that I'm graphing two lines, and I mean them to be the same line. So every point on one line is also a point on the other line, but they're the same line. So this system has infinitely many solutions. And since it has at least one, it means it's consistent. A consistent system. Okay, then the third case is if there's no solution. And this has already been alluded to. If two lines are parallel, they never intersect. So when we say parallel, we're saying that the two lines have the same slope, but they have different y-intercepts. And since the two lines never intersect, the corresponding system of two linear equations has no solution. This kind of system is referred to as inconsistent. And a little bit later, it will perhaps make more sense why the word inconsistent is used. Okay, in the next couple of examples, we'll see if we can solve the systems of equations by graphing. Well, when you solve by graphing, well, if you're not a very neat grapher, then you might come up with a solution that's not really the correct solution. So I'll do my best. So we'll graph each of the two lines and see what we get. So for the line whose equation is on top, let's find a couple of ordered pairs. Okay, so if I pick x to be 0, then I'm left with 4y equals 8 or y equals 2. So the ordered pair is 0, 2. 0, 2 is this point. And let's see, this time I'm going to pick x to be 4. So when x is 4, then I have -4 plus 4y equals 8. If I add 4 to both sides, I get 4y equals 12. And so y will be equal to 3. So I get the ordered pair 4, 3. So I'll go ahead and plot that point. So this point, 4, 3. I'll label these a little bit later after I graph the other line, but so I'll make this line blue. Okay, now let's find a couple of points on the other line. So we need 2 ordered pairs. So on this one, let's pick x to be 0. And when x is 0, 4y equals -4, so y equals -1. So we have the ordered pair 0, -1. So this point, and let's go ahead and make the y-coordinate 0. And then we have 2x equals -4, so x equals -2. So this is -2, 0. This point. So on this one, I'll use the green ink. So they intersect. Okay, this ordered pair is 4, 3. This one's 0, 2. This one is 0, -1. And that one is -2, 0. Okay, well, what does it look like the coordinates of that intersection are? So it sort of looks like it could be -4 for x and +1 for y. But we don't have to leave it to chance. We can check to see if this ordered pair is a point on each of the 2 lines. Right? If the 2 lines intersect at -4, 1, then -4, 1 has to be a point on each line. So why don't we go ahead and check that up here? So when x is -4, the negative of -x is the negative of -4, which is 4, and then plus 4 times 1 is 4. And does that equal 8? That's true. So let's check the bottom line also. 2 times -4 is -8, and then plus 4 times 1 is plus 4. And -8 plus 4 equals -4. That's also true. So we verified that the point of intersection is the ordered pair -4, 1. So what does that mean? It's a solution to the system. -4, 1 is a solution to the system of 2 linear equations. Okay, so those are all synonymous. -4, 1 is the point where the 2 lines intersect, and -4, 1 is the only solution to the system. Okay, to be complete, I should write -4, 1 is the solution to the system of those 2 linear equations. But I'm abbreviating it here because of lack of space. Since there's one solution, the system is consistent. So one reason that consistent is used is because the word consistent coincides with a true statement when we verify that we have a solution. So in other words, something that's true is consistent with reality. Let's look at the next example. Let's solve this by graphing. So this time, I'm going to find, before drawing the graph, I'm going to first find 2 ordered pairs of points that are on the top line. So we want to find the ordered pairs of 2 points. Okay, so if we pick x to be 0, then -3y equals 6 means y is -2. So the ordered pair of that point is 0, -2 in parentheses. And then if we let y be 0, -3x equals 6 means x is -2. So we have the ordered pair -2, 0. Okay, for the bottom line, we'll find 2 ordered pairs of points on that line. Well, 18 is kind of a big number, so I'm going to find numbers that aren't that hard to graph. So let's see, if I pick x to be -3, so the negative of -3 is 3, and if I subtract 3 from both sides, I'll get 3y equals 15, and then divide both sides of that by 3, I get y equals 5. So the ordered pair -3, 5 And I suppose if we let's just go ahead and let x be 0. And when x is 0, 3y equals 18, so y equals 6. So the ordered pair 0, 6 is a point on the graph. So the ordered pair 0, 6. 6 is kind of big for the space we have, so the tick marks will be kind of small. There's 0, 6 for this line, and negative 3, 5 is this point. So we'll draw a straight line through those 2 points. And the other line, 0, negative 2, and negative 2, 0. So now we draw a line through those 2 points. Okay, I'll label these points. This is 0, negative 2, negative 2, 0, 0, 6, and negative 3, 5. Hey, well, what could the ordered pair for that point of intersection be? So you see the dilemma we have. If our graph is not extremely accurate, or at least accurate enough, we might have a hard time solving by graphing. So perhaps, so maybe it's negative 5, 4, negative 5, 4, question mark. We do know that the lines intersect, but we should check to see if negative 5, 4 is the point of intersection. So if we check the ordered pair negative 5, 4 in the top line, negative 3 times negative 5 is 15. And then minus 3 times 4 is 12. 15 minus 12 equals 6. That's false. So the answer is, well, that's not the ordered pair of the solution. But there has to be a solution. The 2 lines have different slopes. Okay, well, we don't have to resort to graphing lines to find solutions to systems. We have algebraic methods which are much better than solving by graphing. So let's look at some examples where we don't have to resort to solving by graphing. Okay, first of all, in these 3 examples of systems of 2 linear equations in the variables x and y, without graphing, determine if the systems of equations are consistent or inconsistent. Okay, a system of two linear equations is consistent if it has at least one solution. So a consistent system has two lines, either the slopes are different, or the other possibility for consistent is that the two lines are the same line. And then inconsistent, the two lines are parallel. So we can answer the questions if we rewrite all equations, to the slope-intercept form. The y equals mx plus b form. If we have y equals mx plus b, then we can tell just by looking if the system is consistent or inconsistent. Okay, so the top equation solve for y, so we get negative 9y equals negative 7x minus 5, and then divide every term on both sides by negative 9, we get y equals positive 7/9 x plus 5/9. And then the bottom line, solve that for y. Subtract 8x from both sides, we get negative 2y equals negative 8x plus 4. And then divide every term on both sides by negative 2, we get y equals 4x minus 2. Okay, so this is the system of two linear equations where each of the lines is in slope-intercept form. So since the two slopes are different, that means the lines intersect at exactly one point. And so the system is consistent. So this is consistent. We're not trying to find the solutions, we're just identifying if the system is consistent or inconsistent. And the next pair of solution, or in the next system of two linear equations, one of the equations is already in slope-intercept form. The bottom equation, y equals 7/3 x minus 8/3. So the top equation, solve for y. So subtract 7x from both sides, we get negative 3y equals negative 7x plus 8. Then divide every term on both sides by negative 3, and we get y equals positive 7/3 x minus 8/3. When two lines are in slope-intercept form, well, it's easy to tell if the lines are the same or different. So these two lines are the same, and so there are infinitely many solutions, so the system is consistent. Okay, the next pair of equations, the next system of two linear equations. To solve the top equation for y, we just have to subtract 6x from both sides. So we get y equals negative 6x minus 4. And then solve the bottom equation for y. First add 48x to both sides. So we get negative 8y equals 48x minus 16. Divide every term on both sides by negative 8. We get y equals negative 6x. And negative 16 divided by negative 8 is positive 2. So these two lines have the same slope of negative 6, but they have different y-intercepts. So the two lines never intersect. That means there are no solutions. So this is inconsistent. Okay, so there are three cases for systems of two linear equations and two variables, x and y. If the two lines have different slopes, the lines intersect at exactly one point, so the system is consistent. A second case out of three cases altogether, if the two lines are exactly the same line, then the two lines intersect at every point. The system has infinitely many solutions, so it's consistent. And the third case out of three cases altogether, if the two lines are parallel, they never intersect, so they have no solutions, which means the system is inconsistent. Okay, in the next little exercise, we have a system of two linear equations. One equation is 2x minus 8y equals 6. The other equation, y equals 2/3 x plus 3. And then we have 5 ordered pairs. And we want to see if any one of those is a solution to the system. So how many solutions does this system have? Since we have three cases, we're looking for answers. One solution, infinitely many solutions, or no solution. So what about this system? The slope of the second line is 2/3. The bottom line is in slope-intercept form. Remember, if two lines have different slopes, then the two lines intersect at exactly one point, so the system will have one solution. Well, if you want, you can rewrite the top equation so that it's in slope-intercept form. So if you solve for y by subtracting 2x from both sides first, and then divide every term on both sides by negative 8, you get y equals positive 1/4 x minus 3/4. The two lines have different slopes. So that means the system has exactly one ordered pair solution. And we just want to see if one of those 5 ordered pairs is the solution. It's possible that all 5 are not solutions, but at most one could be, because this system has just one solution. Okay, so let's get started with 4, 0. If we replace x with 4 and y with 0, we get 0 equals 2/3 times 4 plus 3. Well, this equation is false, so that means it's not a point on the top line. So this point is not a solution. As soon as you get an equation that's false, you don't need to test any further. Okay, the next point, 5 1/2. This time, replace y with 1/2 and replace x with 5. So 1/2 equals 2/3 times 5 is 1/2 equals 10/3, and then plus 3. Well, this can't be true. The right-hand side is bigger than 1/2. So this is false. Okay, the next ordered pair, if x is 5 and y is 19/3. So in the top equation, replace y with 19/3, replace x with 5. 2/3 times 5 is 10/3. This time we get a true statement. This is true. But in order for this ordered pair to be a solution to the system, it has to also be a point on the other line. So we have to test this ordered pair with the other line. So we'll replace y with 19/3 again. And replace x with 5. So 1/4 x is 5/4. And 5/4 minus 3/4 is 2/4, or 1/2. 19/3 equals 1/2 is false. So even though this point 5/19 is on one of the lines, it's not on the other, so it's not a solution to the system. Okay, the next ordered pair, 1/3 -7/4. So in this equation, y equals 2/3 x plus 3. Replace y with -7/4. And replace x with 1/3. So 2/3 times 1/3 is 2/9. And then plus 3. We're using this equation. This is false. The left-hand side is negative, the right-hand side is positive, so that doesn't work. Okay, so does that mean we can conclude that this fifth point is a solution? Not necessarily. We're not guaranteed that it's a solution, so we still have to check. So we're going to check -9, -3. So in the top equation, in this equation, y equals 2/3 x plus 3. Replace y with -3. And replace x with -9. 2/3 times -9 is -18/3, and then plus 3. Or -3 equals -6 plus 3. That's true. But we have to test this point on the other line also. So the other equation, y equals 1/4 x minus 3/4. Replace y with -3. And 1/4 times x is 1/4 times -9, or -9/4. And -9/4 minus 3/4 is -12/4, which is -3. This is also true. So -9/3 is a solution to the system. Okay, the next little exercise will be a little easier because we're just given one ordered pair, and all we need to do on this one is determine if this ordered pair is a solution to the system. Okay, so in the top equation, replace x with -11 and replace y with -9. So 2 times -11 minus 3 times -9. We want to know if that's equal to 5. So we'll do the arithmetic. -22, and we're subtracting -27, which is plus 27. And -22 plus 27 is true. So we do know that that ordered pair is a point on the top line. But in order for it to be a solution to the system, it also has to be a point on the other line. So in the bottom equation, -3x plus 3y equals -6. Replace x with -11. So we get -3 times -11. Replace y with -9. So we're adding 3 times -9. We want to know if that's equal to -6. -3 times -11 is positive 33. And 3 times -9 is -27. So 33 minus 27 equals -6. Or 6 equals -6. That is false. So -11, -9 is not a solution. Okay. All right, we have a few more. Solve the systems of equations by graphing. Okay, graph each of the two lines. So let's find a couple of ordered pairs for the top equation. Well, I would like to avoid numbers that are too big so that they're easier to plot. So maybe if I pick, looks like I'm going to get big numbers, fairly big numbers anyway, but if I pick x to be 6, 6 divided by 2 is, whoops, maybe, yeah, okay. I guess we're just not going to get around it. 6 divided by 2 is 3. 3 minus 10 is -7. So the ordered pair 6, -7. And then one other ordered pair. So how about x is 4? 4 divided by 2 is 2. 2 minus 10 is negative 8. So 4, negative 8. And then the bottom line, find a couple of ordered pairs. If we pick y to be 0, then negative 4x equals negative 8. Divide both sides by negative 4, we get the ordered pair 2, 0. That's not too bad. And then one more ordered pair. Well, if I pick y to be 4, that won't be too bad. So negative 4x minus 4 equals negative 8. Add 4 to both sides, we get negative 4x equals negative 4. Divide both sides by negative 4, I get positive 1. So I want to double check when x is 1, that's negative 4 minus 4. Okay. So we can plot these points. Okay, so one of the points is 6, negative 7. And then 4, negative 8. So roughly, there's that line. Then the other line, we have 2, 0. Whoops. No, that's right. 2, 0 and 1, 4. And then draw a straight line through those 2 points. So this ordered pair is 1, 4. This one is 2, 0. This one's 6, negative 7. This point is 4, negative 8. So I don't know. Could it be that 4, negative 8 is the point of intersection? So I already fouled up one solved by graphing. So let's check 4, negative 8. Well, we already know that 4, negative 8 is on the top line because that's a point on that line, right? So now we'll check it in the other line. So replace x with 4, so we get negative 4 times 4 is negative 16. And subtracting negative 8, does that equal negative 8? So negative 16 plus 8 equals negative 8. So that is true. It looks like 4, negative 8 is a point on both lines. Yep, so that's the solution for negative 8. Okay, we're about out of time. The rest of the exercises here are like the ones that we've done before. So this next one, solve this by graphing. And then we have, below that, we have three systems of two linear equations. Determine if the systems are consistent or inconsistent. So my suggestion is rewrite each of the equations in slope-intercept form first, and then you can tell just by looking whether the system is consistent or inconsistent. And that's all we have time for today. So go ahead and sign in for attendance.